Alright, we're going to begin now with questions on the homework, which I believe homework is 12.4 and 12.5. Yep. 12.4 first. Yeah.
Number 9 is 12.4, second edition.
Yeah, I think the homework was very, very similar between the first and second edition for 12.4.
You have to flip back since 12.5.
Okay, so number 9 says find the mass and center of mass that occupies the ball. Okay. One more. Here D is given by all xy such that okay, so we want to find the mass and the center of mass for the lamina that occupies the given region with this density function. So what is what's the formula? How do we get to the mass? It's the double integral over d of rho. That's it. So we're just going to set up this double integral. So what does this look like? Well, they sort of gave you the limit, so you're just going to set it up. It's like 0 to L and 0 up to sine of pi x over L. Of rho, which is y, this is dy dx. Right? L is just a constant, so you just, that would be the limits on the outside. And so that's how you set it up, and you do that in, which, what was it here? This is going to be just y squared over 2. And you're going to plug in sine squared pi x over L. Right? And then, how do you integrate the sine? Yeah, change it by the half angle or double angle form. Depends on how you want to look at it. Which gives you another half, which makes this a quarter, 0 to L of 1 minus cosine of 2 pi x over L. So the period of this is actually L, so this is actually going to give you 0, so you don't have to worry about it. And so this would just give you L over 4. Right? So that was the mass, L over 4. Whatever L happens to be, that's going to be, divide that by 4, you get the mass. So how do we find the centroid? By the way, what does this thing look like? If you graph D, what would it look like? When x equals L, what do you get?
Sine of pi,
Which is?
which is 0.
0. So when x is 0, you just have 0. And then it goes up, because that like sine goes back, and it's 0 again when you hit L. Right? Which means we should be able to use symmetry here. Right? The peak is going to be at what? X equals L over 2. Right? remember that the point you're looking for, the center of mass, is the point that balances, right? So notice that on the x-axis, the balancing point should be at L over 2. And we just have to figure out the y value, right? So we're really looking at the point where we can sort of balance this thing. The problem is the density is given by the y value, which means it gets heavier as you're going to the top, right? So the higher up you are, the heavier that your density is. So that's sort of the weird part. So really it's the vertical that we have trouble with. The x will sort of be the same. So I already know that the x bar should be L over 2. Now I really only need to find the y bar. The formula for y bar is 1 over m times the double integral over d of y times rho dA. So then 1 over m is just 4 over L times 0 to L, 0 to sine pi x over L. And rho was y, so this is just y squared dy dx. And this is pi c. Now I do the same thing, but now I have y squared. And so now I'm going to integrate that. This would be y cubed over 3 here, and then this would be sine cubed pi x over L x. How do you integrate sine cubed?
Sine squared times sine.
Right, write as sine squared times sine, then change the sine squared to 1 minus cosine squared, and then do a substitution equals cosine. All right, so that's what we're going to do. So this is 4 over 3L, 0 to L. This is going to be 1 minus cosine squared pi x over L times sine pi x over L. Let u equals cosine u be minus sine L over pi. Plug in L here, you just get plug in L for x, you just get cosine of pi minus 1. This will give you minus 1, that plus minus, plug in 0 for x, get cosine of 0. That gives you 1. Sign is off somewhere. Yeah, that should be positive. Did I make a sign error or something? Come again? What? This is fine?
Yeah, that's fine.
You want the minus sign here?
It's minus -2, so it's -2 plus 2/3.
Oh, yeah, okay. I thought it was a minus here. Okay. All right, we're fine. It's 2/3 minus 2. Okay, that makes sense. 2, I just write it as 6/3. Alright, so this is minus 4/3 and that's your y bar. So this means mass is L over 4, and the center of mass is L over 2, comma 16 over 9. Okay, questions? Right. What? Because of the symmetry, so I didn't need to solve for x bar. Had I done it, I would have gotten L over 2. But remember, the center of mass is trying to find your balancing point, theoretical balancing point, which I could see by symmetry, it's really going to balance here. The only question was, where is the vertical position of the point? Because your density is changing as the y changes. Right? So the upper half is heavier than the lower half, so it's sort of like, where do you balance that? So I figure out the x by symmetry, and then the y I had to actually do the computations. So this will actually show up often. They'll actually put in the question where you can use symmetry to figure out the function, right? Because as you can see, really what 12.4 comes down to is memorizing these formulas, right? Everything else is just evaluating integrals. So asking you one of these questions just actually evaluate a bunch of integrals. So if I want to test if you can evaluate integrals, I'll just give you something where you only have to do one integral, and then the other ones just get by symmetry.
I don't get how that's little get how the symmetry.
Well, it's this half and this half is exactly the same, right? It's exactly the same. It's a sine.
Oh, okay.
It's a sine curve, right? Which means it repeats the same pattern, right? And the time it takes to go up is time it takes to go down, right? So I know it's exactly the same, right? So I didn't just assume this is symmetry by how I graphed it, right? Because of course when you're drawing by hand, you're not drawing to scale. But knowing that it's a sine graph, or usually they'll put like a part of a circle or part of some equilateral triangle, they'll give you something where you should know that there's symmetry.
How do you know L is 0?
Come again?
How do you know L is when y is 0?
I know it goes from 0 to L, and this is the function, sine, right? So my region is from 0 up to this graph, right? So that's the region. This is D. And I know when x is 0, sine of 0 is 0. When x is L, I get the L's cancel and I get sine of pi, which is also 0. So I know I hit 0 again by the time I hit L. So I know 0 to L, that's the whole thing, but I have symmetry, so halfway there is going to give me that L over 2, that's going to give me x. The y I had to figure out. Yeah. Other questions? In the same section?
Yeah.
I mean, so here D is bounded by what? So these are similar. I can set up the integrals, but I don't really want to waste time doing the integrals. So for this one, you're also going to have symmetry. Upside down parabola, it's between -1 and 1. So again, we have symmetry here, right? I can tell right away x bar is going to be 0. This is my region. So now I want the mass and center of mass. The mass is going to be, it's just going to be the double integral over d of the rho dA. This is going to be, rho is k times y. Okay, how would I set up the limits here? Yeah.
You assume that it's symmetric because the density function.
Because of the density function, right?
Because
If I had a density function that changed according to the x, that's a
then you can't assume.
right? I said that over there, but I said it pretty fast. I don't know if anyone catch it. Cannot assume symmetry if density varies with respect to x. Right. So the reason is, in that case, you might have one side that's heavier than the other side as far as the x is concerned. And so you wouldn't be able to balance by going right in the middle. But because my density is changing by the vertical level, right, horizontally everything is the same all the time. But what would the limits be here?
Negative 1 to 1. And that
Okay,
would
so I
be
assume
your
you're telling me
dx.
the outside integral.
Yeah. And then 0 to
0 to 1 minus x squared. Okay, so this is dy dx. And I assume we'd be able to do that once you set it up. And since we already know the x bar, the only thing left again in this case is the y bar. Y times rho a. So this would give me whatever I got for x. And it's going to be minus 1 to 1 of 0 minus x squared of ay squared dx. Of course. So this gave you the answer A, and that gave you the answer B. Then let's go to 12.5. It's a more interesting section. On 12.5?
Yeah.
Yeah, so 12.4, it's just integration again, except in this case you're applying it by applying a certain formula. And sometimes they set it up so that symmetry can help you out, but there's nothing much else going on. And you use the first.
1. Do you want me to bring up the first condition on that?
No, I usually just grab it. Okay, express the triple integral as an iterated integral in 6 different ways. Where E is a solid. Okay, this is good for instruction purposes, I guess, but in practice, in like an exam, I could actually just set up an integral in several different ways, but it would be by coordinate systems rather than by the same coordinate systems and different perspectives. Right? So I might actually just set something up in rectangular and cylindrical and spherical. By the end of today or tomorrow, you'll know what all those are. But yeah, this is just different views within the rectangular coordinate system. Z equals 0, Z equals Y, squared equals 1 minus. Okay, so you want to express full integral over e of f of x, y, z, in 6 different ways. What are the different ways they would be talking about?
Orders of integration.
The orders of integration. So it could be dx, dy, dz, or you can set it up as dx, dz, dy, or you can set it up as dy, dx, dz, or dy, dz, dx, or you can set it up as dz, dx, dy, or dz, dy, dx. Right? So they want you to set up 6 integrals with these different orders. But remember, when you're changing the orders, the functions, the way you express the functions will have to change as well.
That's what I found.
So that's going to be the issue here. So first, let's actually graph our region to see what it looks like. Can we actually draw that? So our y is actually 1 minus x squared. Z goes from 0 up to y. So 1 minus x squared, so that's going to be like a parabola. Z is going from 0 to y. So by the way, z equals y in the yz plane. It's just a straight line like this, right? And if I look at y equals 1 minus x squared, what that looks like is it's a parabola like this. Let's go with
Parabolic cylinder.
it's a parabolic cylinder.
So it chopped up across at 45 degrees.
Right, so I cut it off on the XY plane,
Right.
flat floor, 0, and then there's another plane slicing this way.
Okay.
Right, so it looks like from another view, it would look like a wedge. Right,
Yeah,
where
okay.
this would be the Z, the positive Y would go that way, and the positive X would go this way. So that's the sort of thing we're looking at.
Okay,
Okay, so the thing is, remember when you're setting up these coordinates, the important thing to remember is the region of integration is given by the 2 outside guys, right? So if we're setting up dz, dx, dy, dx, dy, dz, my region of projection has to be in the yz, right? Which in the yz plane, this would actually be a triangle. If I'm looking in the xy plane, my region is actually a part of the parabola. If I'm looking in the xz, what would it look like?
It would also look like a curve.
What would it look like in the xz? Exactly the same, right? Because at that point, z is equal to y, so I can literally just replace the y with the z here. Right, now knowing those 3 different views are essential to being able to set up the integral, right? So when you're looking at, you're going to need to know what this is in order to set up dx, dy, dz, and dx, dz, dy. Right? This guy gives you the double integral part. This you're going to need to know for dz, dx, dy, and dz, dy, dx. This guy you have to know for dy dx dz and dy dz. But once you figure out, so those guys give you the double integral region. That's where you're projecting things. Okay, so I mean, let's start. First one was the x, y. So I know that this is right here. This goes from 1 to 1. This goes to y. So how would it look?
Okay, so the x is the surface, a pair of surfaces.
Let me see the two outer ones first. I want z to be on the outside, right?
Right.
Which means my z is going between constants.
Right.
Now what are the constants? Just 0 to 1. Now if I want my y to go between functions, it would go from what? 0 to z. So then this would be 0 to 1, 0 to z. And my x goes from 1 to 1.
This is square equals 1 minus y. Negative root 1 minus y to square root 1 minus y.
All right, you can solve for the x here. All right, it's going to be this plus or minus the square root of 1 minus y. So the minus square root is going to give you that left side, and the positive square is going to give you the right side. Now if I'm looking at instead dx, dz, dy, the only difference is here I want to switch these two, right? Let y go between the constants and let z go between the functions. So I would have y goes between 0 and 1, and z goes between 0 and y, and everything else would stay the same. So this would be 0 to 1, 0 to y, minus 1 minus y, positive 1 minus y, and x, y, z, x, z. If I wanted to do dy dx dz. Okay, so where's my region of integration? What am I looking at?
Looking at the x z point.
Right, dx, dz are on the outside, which means this is the region of projection that I'm looking at. Which means I can express this in two ways. If I want my x to go between constants and the y, the z to go between functions, or vice versa. Let's do both of them. So how do I set up my limits for this one?
Z is going between 0 to 1.
Right. X goes from
X goes from negative root 1 minus
in this case I would let x go from -1 to 1. z would go from 0 up to 1 minus x squared. And so I can set up the integral as, let's do this one first, 0 to 1 minus 1 minus z up to 1 minus z. Another integral of x, y, z. This would be dy dx dz. Or I can do minus 1 to 1, 0 up to 1 minus x squared, something x, y, z, y, z, x. What are the y's going to be?
0 to z on the y-axis z.
We're projecting here, right? Right? Which means my y is going to be described by the bottom surface and the top surface.
Right.
What's the bottom surface?
Bottom surface is at 0.
No, if it was 0, it would be on the xz plane.
I'm sorry, you're right. It's z.
The bottom surface is the z.
Right.
The top surface is the parabola, the parabolic cylinder. So this would go from z up to the parabolic cylinder, which is, what is it?
1 minus y.
1 minus x squared. Well, that's to our similar. Do I have to do them, or are you guys getting it? So it depends. So again, what you should take away from this is when you want to set up something a certain way, the two guys on the outside tell you what plane you should take a projection. Right? So when we're looking at the last one, dy dx dz, I want my projection to be in the xz plane, which means that's where the shadow is. And then I'm looking at what surface, as I'm going along the y, are my bounds. The lower surface was this slanted plane. The upper surface was the parabola, the parabolic cylinder. And that helps me to set these guys up. Other questions on 12.5? Come again?
Number 9, second edition. It's an example of my superpower.
So
You got it? Did you get it with the arc? Yeah, I got it with the arc. 9503. He also did it.
So this is saying evaluate E of Z over X squared plus Z squared. E, where E is given by X, Y, Z. One less than Y less than 4. Y less than Z less than 4. X is less than Z. over x squared plus x squared plus 4 z minus 4x plus 0. Okay, so how do we set up this integral? I mean, just using what they gave us. You could set up with the y on the outside, the x. Is that how you guys tried to do it?
We tried to do it. Keep going.
I mean, you could do an arc, that would give you arc sine. I mean, integral with respect to z first, you get an ln. Arc tangent, yeah.
Yeah.
Is there a way to do it without that? Like, do you
Once-
have to use that, like, that particular trigger?
The particular what?
But do we have to use arctangent? Or
Yeah,
Because-
is there a way to do it like with one horizontal, or is that something else?
To do this with polar coordinates? Well, I wouldn't advise it, because then that would mess up your limits. See these nice limits you have here? In polar coordinates, they wouldn't look so nice. You get trig functions in your coordinates, and this would turn into a radical or something. So it's probably not worth the switch. Polar coordinates is nice when your region of projection is a part of a circle. So you might be able to simplify here, but then out there you're going to have trouble. I wouldn't waste the time. So yeah, I would just do it with the arc tangent. So this is going to be but instead I get tan inverse of 1 is what? It's just power of 4. And then we're going to integrate power of 4 with respect to z. This is power of 4 z between y and 4. Plug in 4, I get pi, minus plug in y, I get power of 4 y. Pi minus four squared is 16 divided by 8. Pi minus 2 pi minus 1 pi, that's just pi plus power of 8. No. You could have switched the order here, and then you get an ln. Right? If you integrate with respect to z first, you could do a u substitution, and you get an ln. I don't know how much easier that was.
It wasn't.
Like tan inverse shows up pretty often, you should remember.
It wasn't easy at all. Just the the record.
Yeah, that's something you should remember. It shows up often enough. Other questions? Yes.
19 is the second.
Use a triple integral to find the volume of a given solid. Could we actually graph that? Is that something that we can graph nicely? I mean, try. Y equals x squared. What does that look like?
It's a parabola. No, it's a paraboloid cylinder.
Parabolic cylinder. Okay, and z equals 0 would be the floor, and z equals 1 minus y, so it's going to, when y equals 1, this I'm going to look at as z equals 1 minus y. So when y equals 1, that's where it cuts off here. And then it's slanting back. Z equals 1, y equals 0. So it's very similar to the thing we had before. It's just a plane cutting through here. So if I had to graph it, it would look like. That's our guy. Okay, so how do we set up volume? Use a triple integral. So how do we find volume by triple integral?
UV.
Huh?
You said it. Triple
What's the general
integral.
formula? Triple integral of 1. You always integrate 1. So you find the triple integral over the solid, you integrate the function 1. That's how you find the volume. So now this is our solid, so we're going to figure out how to set up the limits for this. And how would we set it up? I can set it up with dx dy as my region of projection. In which case I'll just have this. In which case I would have y equals x squared is the bottom, y equals 1 is the top. Right, so if I look in the xy plane, that would be my head. Okay, so now I can just have
X
x
goes
over
from
minus 1
-1
to
to
1, y
1.
goes from x squared up to 1. And my z goes from 0, which is the floor, up to the plane 1 minus y. Of 1 dz dy dx. Notice here this is an even function. I actually have symmetry here. So I can actually double up, but I can get to that. Right? We could actually find half of this and double it. Right, so I could, let me write that. 2 times 0 to 1. Now, hopefully once he set this up, the rest won't be so bad. This is 2, 0 to 1, x squared up to 1. Integrate this, you get z, you plug in 1 minus y and 0, so this is just 1 minus y. Integrate that with respect to y, you get y minus y squared over 2. This is going to go from x squared up to 1. If you plug in 1, you get 1 minus a half, which is just a half. Minus, if you plug in x squared, you get x squared minus x to the 4th over 2, but that becomes a plus. So then this is 2 times x over 2 minus x cubed over 3 plus x to the 5th over 10. 0 and 1. That's just going to be 2 times a half minus a third plus a tenth. Which is what? What? It's what? What did you say?
4 by 15.
4 over 50. Questions on the setup? Because I think getting to this point is probably the hardest part. Most of the work is getting there. So any questions on getting there?
Yeah, how did you, oh, I see. Never mind. I was going to say, where did that 2 come from?
Yeah, because I think this one.
Yeah.
I just said about half of this.
Does it make a difference if we just get the negative over 1 or is it the same?
No,
Okay.
would have been the same.
Are there any cases where with negative 1 or whatever,
Yeah, if this thing changed in the x direction, that would be bad. Right, but because notice that as long as you're moving horizontally, all these cross sections here, you're at the same height the whole time. Right. So if this thing was like turned that way, you couldn't double up on the x. Yeah. But again, a lot of times it's nice to be able to draw the object, figure out where you want to project, and that's going to help you set up the 2 outside integrals easy peasy. And then the rest is going between the 2 surfaces. Oh, I doubled. I realized that this thing is like, I can find half of this. It's exactly the same. So I just looked at this. I just looked at half. So I just let x go from 0 to 1, and then double the answer.
Is this the answer after you double?
Yeah, that's what you told me.
I thought
Oh, you just told me the inside?
Yes.
Yeah, I want this times the 2. Other questions? 15? 15, 1-5. Second edition? So the setups are the hardest part. I mean, if you guys have time, you should probably go back over the homework and try to even set up the even problems. You got a lot of practice with the setup because that's the biggest part. The rest of it is like mechanics, and it feels like block 2. It's the setup that's the hard part. evaluate the triple integral. E bounded by Okay, so how do we do this? First of all, what is this? What is this about?
Your parabola coming out on the x-axis.
So the parabola is coming up towards the x-axis.
And
It's
x
going to be
equals
cut off
4.
by the plane x equals 4. So this is that. So this is x equals 4y squared plus 4z squared. This is x equals 4. Prior region projection into the yz plane would be the best thing to do. So I try to project this into the yz plane. It's obviously going to be a circle. So that's my region D. What's going to be the radius of the circle? 1. Because it's where x equals 4 intersects this, right? So intersection. X equals 4 plugged into that, you just get 4 is equal to 4y squared plus 4z squared, which means y squared plus z squared equals 1. And so that's the equation here. Okay, so now with that set up, how do we, so the yz, let's have a circle here. This one.
I took this one into polar coordinates.
Yeah, it's technically polar coordinates in the next section, so you can't do it. How do you set it up in rectangular?
Y goes from negative 1, z goes from negative square root of 1 minus plus 0.
You said y from minus 1 to 1, and z from minus 1 minus y squared up to 1 minus y squared. And the x would go from, what's the bottom surface for the x? This is the bottom, right? So this is 4y squared plus 4z squared. And the top is the full length for this is x. This is the x, z. So that's one possible step. Later on today, we're going to be able to set this up in what we call cylindrical coordinates, which means we think of the two outer integrals as being given by polar coordinates, right? Where we can realize that the circle is 0 to 1, or 0 to 5, 0 to 1, are the x would go from 4r squared. So that's later today we'll be able to do that. So this is just thinking of the y and the z as in polar coordinates, so I can set them up according to the polar limits, which gives me these two outer integrals and the r dr d theta. Then the x is just remains x, right? When you do this sort of manipulation, it's called cylindrical coordinates. And we are going to do that later today after the break, 10-minute break. And we go to the next section. Leave your homework